So welcome everybody to the first session of this series of lectures. We have had a lot of very interesting talks on heavy ion physics in lecture series across the world in the last 2 years. And I think it's probably the right time with so many experiments coming up to have also a series in which we look at the details of experiments, try to compare what the different experiments are capable of, and therefore what kind of measurements they're able to make more sensitively, and so on. Okay, so these are questions that we will address through this set of lectures. The format, as you know, will be the following. We take one topic, like today we are starting the topic of particle identification, and then we have people from different experiments talk about their experiment, the details of their detectors, how that affects the kind of physics that they can do, and so on. And we have a series of talks from different detectors on the same topic. And at the end, we'll have a session where all of them come together and we'll have a discussion on the specific differences between different experiments. Okay, so for particle identification, we start with Chitrasen Jena giving a talk on PID at star today. In all these talks, the speaker will have 1 hour to speak. And during that time, please keep your questions to the absolute minimum that is necessary to understand what's going on. Because at the end of every session, we have planned a half hour of questions, which we can extend if we need to. And you can ask questions at that time. Any detailed questions, any further elaboration that you want can be asked at that point. Okay, so we will also be keeping track of the questions so that the same questions can be asked to different other speakers if you wish, and so on. At the end of the talk, we'll have some questions recorded. Then we will stop the recording so that people who want to ask questions but don't want to be recorded can also ask at that point. Okay, so with that, let's start. So Chitrasen, the floor is yours.
Okay, thank you, Solenoidal. This is a very nice initiative to discuss details about the experimental parts and the physics part. So I would also like to thank the organizer for giving me the opportunity to talk about particle identification at star. And I think this is a very difficult task, but I'll try to manage. So with time also the detectors evolves, and time to time there is some upgradation or some new detectors comes. So but in this talk I'll try to focus on the major detectors, and the organizer wanted me to also compare with the system which is used in star is very similar to ALICE. Then some of the cases I will also compare with ALICE. So with this, let me start my talk. So here is the outline of talk. So before going to experimental part, I'll give a very general introduction about the heavy ion physics, introduction to heavy ion physics, basically talk about the QCD phase diagram and the evolution of heavy ion collisions. Then, as I said, I'll talk briefly about star and ALICE detector systems in general. Then we'll go to very specific to the particle identification. The major particle identification major detectors are time projection chamber and time of flight. And then I'll also talk about a photon multiplicity detector, just for this is also another detector which is used for the identification of photons. This is time projection chamber and the time of flight. So is there any message? I cannot see the message.
No, as far as I know, there's no message here. But since you asked, I'll also take the time to tell everyone that any questions for later, they can also write in chat boxes, both on Zoom and on YouTube. People are monitoring that and will relay the questions to you when the time comes. Thank you.
Okay.
Please continue.
Okay, thank you. So let me start with the QCD phase diagram. I think all of you are very familiar with this. Let me start. Because the heavy ion collision program which we do at a LHC, Large Hadron Collider, or the relativistic heavy ion collider, it is to explore this QCD phase diagram. So QCD is nothing but quantum chromodynamics, which is the theory of strongly interacting matter. And then this is QCD phase diagram actually usually plotted as a temperature versus baryon chemical potential. And in this diagram, if you look at a low baryon chemical potential and a high temperature regime, which is zero baryon chemical potential is the one which is the LU inverse case. And then LSC and RHIC at top energy, they try to explore very close to that situation, very zero baryon chemical potential region and a high temperature region. But at with this motivation at LSC and RHIC top energy, it was started. There we also try to see. So at this high energy and low baryon chemical potential, we expect there is a phase transition from a normal hadronic matter to a quark-gluon plasma, and that is that deconfined state of quarks and gluons. To study that properties of that, we need this type of experimental facilities. So in addition to that, at RHIC also, due to the polarized proton-proton collision, we also try to explore at a high energy proton-proton collision proton spin structure. And recently there is a lot of interest to explore this QCD phase diagram in a high baryon chemical potential and low temperature region, because as we know, the lattice, the QCD calculation suggests that at a high baryon chemical potential and a low temperature, there is a fast order phase transition. And then this is at a high temperature and a low baryon chemical potential, it is a crossover. So that means at some point this fast order phase transition ends, and that is called as a QCD critical point. And to explore that that part of the phase diagram, usually RHIC is a very versatile collider, so which can vary the center of mass energy, and it can go starting from 200 GeV, it can go to 7.7 GeV. Already we have taken the data in the collider mode up to 7.7 GeV, and also in the fixed target mode, you can go up to center of mass 3 GeV. With that, we are trying to explore this region of the phase diagram to search for a possible QCD critical point, as well as to see if there is a turnoff of a signature at a certain center of mass energy. So that is the beam energy scan program. And that, as I said, it is extended again. Instead of a collider mode, you can use RHIC as a fixed target mode, and then explore a high baryon density regime, which is mentioned here. So then what we do in heavy ion collisions? So in experimentally, so basically we are trying to collide two ultra relativistic heavy ions. So when the bunch of heavy ions actually we try to collide, so that there will be at least one collision will happen. When this collisions happens, so what first it will go through a pre-equilibrium phase, then it will transform this to a quark-gluon plasma phase, or the deconfined stage of quarks and gluons. Then as the system expands and it cools down, it will go through hadronization. And at some point, as the system expands at certain temperature, the particle inelastic collision among these hadrons will stop, the particle production will stop at that point. Then further as the system expands, the elastic collision also stops at a point which is known as the kinetic freeze out surface, and where the inelastic collision stops, that is called the chemical freeze out surface. So so after that, once the kinetic freeze out happens, the particles are freely streamed to the detectors. So that is why it is important to understand this, to study these particles, so that we can understand the initial stage. There is no direct way we can probe this quark-gluon plasma phase. So basically to understand, so we have to rely on the indirect signatures of the quark-gluon plasma by looking at the final state particles. So that is why this final state particle first to reconstruct those particles, and then measuring their properties of these particles will give you several indications or signatures of a quark-gluon plasma. That is what we try to do in heavy ion collisions at relativistic heavy ion collider and Large Hadron Collider. So there are two experimental facilities, as I said. So one is the relativistic heavy ion collider, which is in operational since 2000, and it has started with 4 major detector systems. One is STAR, which is at 6 o'clock, then Phoenix at 8 o'clock, and Phobos at 10 o'clock, and then Brahms at 2 o'clock. There are 4 experiments it started, and slowly Phobos and Brahms they decommission, and later Phoenix also decommission, but that is getting upgraded to S Phoenix now, and STAR is still taking data. So as I said, relativistic heavy ion collider is a versatile particle collider. It not only collides heavy ions or proton-proton hadronic collisions. So in proton-proton also, it does the polarized proton-proton collision to study the spin of the protons. And it also collides various species, starting from proton-proton, proton gold, D gold, and copper gold, copper, and then isobar collisions recently happened. Then uranium, gold, and several collision systems happen. These are actually collisions proposed considering different physics interests. And then, as I already introduced you, the center of mass energy of these collisions also we vary. From top energy 200, we can go to lower energy in the collider mode up to 7.7. And now we have a overlap energy also in fixed target mode, starting from 3 GeV lowest to 7.7 GeV. So that means we can actually, from the relativistic heavy ion collider, we can vary the center of mass energy from 3 to 200 GeV. So then Large Hadron Collider, and in Large Hadron Collider, actually there are also 4 major experiments are there. So one is ALICE, which is a dedicated heavy ion experiment, and then Atlas and CMS, mostly focusing on proton-proton collision, and then also some heavy ion physics they used to do, and then LSCB for B physics, this is specially designed for that. So this Large Hadron Collider, this is the world's currently largest and highest energy particle collider. It does collisions of proton-proton, proton-lead, lead-lead, and xenon-xenon collisions. Till now, it has collided this species. And then the center of mass energy for proton-proton starting from 0.9 tera-electron volt to 13 tera-electron volt already achieved. But it is designed for center of mass energy for proton-proton collision 14 TeV. And lead-lead collision, it has taken data at 2.76 TeV and 5.02 TeV, but it is designed to reach the center of mass energy 5.5 TeV. And the P-lead collision, it has taken at 5.02 TeV and 8.016 tera-electron volt, and xenon also 5.44 tera-electron volt. These are the data sets already collected in run 1 and run 2. Now it is going to start the run 3. So as I said, once we do this collision, relativistic heavy ion collisions, so you can see the number of particles produced are enormous amount of particles are produced, almost thousands of particles in one event. And so here the left side figure, actually, if you see this one, this is the ALICE event display for lead-lead collision at a center of mass energy 2.76 TeV. And this is the event display. Basically, all the tracks reconstructed inside TPC is shown here. So then similar event display is also shown from the STAR experiment, where it is for the gold-gold collisions at a center of mass energy 200 GeV. So these relativistic heavy ion collisions produce thousands of particles. So it is always challenging to develop a detector system which is capable of simultaneously reconstructing these tracks as well as identifying those tracks. So that is why there are several detector subsystems which are employed for different purposes. So some of these subsystems we will discuss. So now let us first start with his solenoidal tracker at RHIC. So this is the star detector. So star detector consists of several sub detectors. So I'll start with some trigger detectors. Trigger detectors usually to trigger the minimum bias events, we have 0-degree calorimeters on both sides of the interaction point. Similarly, beam counter also in both sides. And also sometimes the electromagnetic calorimeter is also used as a trigger detector. In addition to that, this electromagnetic calorimeter is also used for the photon and the pi zero analysis. So then the time projection chamber is the one which is actually the main tracking device in the star detector. So which covers a pseudo rapidity range of ±1. So this is, as I said, it is a main tracking device as well as it does tracking. And once you do the global tracking, then one can project those tracking to reconstruct the primary vortex of these collisions or where the collision happens, that vortexing can be done. Also, by measuring the specific ionization energy loss, one can identify the particles in the time projection chamber. The other detector, which is complementary to the time projection chamber for the particle identification, because particle identification through ionization energy loss has a limitations, because you cannot measure at a intermediate PT region, all the particles will lose similar amount of energy. So that means it is very difficult to distinguish between the particles using time projection chamber alone. So then there is a time of flight detector. I will discuss in more detail about these two detectors, which also covers a pseudo rapidity range 0.9 plus minus 0.9, and it is used for the particle identification. And then, as I said, there is another detector which was a photon multiplicity detector. So that was in the forward rapidity. So minus 3.7 to minus 2.3 in the eta region. And this detector was mainly used for identification of the photons. For the photon measurement, this detector was used, and this detector was completely designed and installed by the Indian collaboration. So then similarly in Alice experiment, so yeah, there are also some other detectors which I didn't mention here, like of VPD. So this VPD is like a upgraded pseudo vortex position detector, which is giving the initial time information for a time of flight, and sometimes it is also used for the vortex reconstruction. And then in the Alice experiment, so Alice experiment has several sub-detectors. So then first let me start with the inner tracking system. So inner tracking system, this is the old configuration. Up to run 2 it was running with the 2 layers of silicon strip detector, then drift detector, and the silicon pixel detector. So each 2 layers of each silicon pixel and drift and the strip detectors are used for the inner tracking system, and its coverage was a plus minus 0.9. So that is the central barrel detector. And it is used for vortexing as well as a tracking. And also sometimes it is also used for the particle identification. It can be used for the particle identification. And then the time projection chamber is also very similar to the star, but this is the largest time projection chamber. So which has a pseudo rapidity coverage from plus minus 0.9. It is used also for tracking and particle identification. And similarly, time of flight detector is also used for the particle identification at the intermediate momentum range. And in the forward detector, there are V0 detectors. So which is usually there are 2 detectors, V0A in the rapidity range 2.8 to 5.1, and V0C, which is minus 3.7 to minus 1.7. And they are mostly used for triggering and also centrality estimator using the V0M multiplicity that is used. And similarly, forward detectors, so there is a photon multiplicity detector, which is in the forward region 2.3 eta range to 3.9. And it's similarly for this is for photon multiplicity measurement, and then there is charge particle multiplicity measurement usually is done in forward multiplicity detector, that is FMD, which is from pseudo rapidity range from 1.7 to 5.0 and minus 3.4 to minus 1.7. And as you all know, this detector Alice is running from 2010 till date. It is taking data, and now it is already run 3 as started. So let me, as I said, I will focus on mostly 2 major detectors, which is very commonly used in the all heavy ion physics experiments. So the time projection chamber, I will try to give first basic principle. So this is the most sophisticated ionization detector which is designed, because as you know, so the gas detector has a long history. So it started with the ionization chambers, proportional counters, and this is the time projection chamber is the one which is usually based on 2 principles. One is the multi-wire proportional chamber and drift chamber. So these 2 mechanisms or the 2 principles are combined together to make a time projection chamber. So it gives a 3-dimensional tracking of all the charge particles passing through this detector material. So usually, as I said, it is a gas detector. So the gas is filled with a thin high voltage electrode at the center. So if you see, this is a schematic diagram. So there is a cylinder at the center, you apply high voltage, and then the readout systems are at the 2 ends. Those are called end caps. And then this when you apply high voltage, and then the anode readout is in the extreme ends, the end caps. So then you make a uniform electric field. So and apply a parallel magnetic field. So the uniform electric field, what it will make, when this charge particle goes through the detector, since this is a gas detector, this charge particle will ionize the gas. Then the electron will try to move towards anode, which is in the end cap, both sides, and then the ions will try to move towards the cathode. But when you apply a parallel magnetic field, so then what will happen? These particles will be curved. Depending on their momentum, they will be curved in a magnetic field. So depending on their curvature of these particles, when you reconstruct the tracks, so once you reconstruct the track, you will know the curvature of the particles. From that, one can calculate the momentum of the particle. That is why time projection chamber not only gives the tracking, but also gives the information about the momentum of the track. And then, so the energy loss which will happen, that will be deposited in your anode. So that will be actually the energy loss in this material will give you the identification of the particles. I will discuss more details about that. So the readout systems here, if you see, so there are anode wires as well as in the y direction, and there are cathode pads which usually gives you the x direction, and you get the xy position from here, and then you project, if you know the time, initial time and the final time will given by this end cap, then this time of travel, actually, if you multiply with the drift velocity of the electron, that will give you the z coordinate. So that is how you can get xyz coordinate, and then you can image the track with different hits. So usually how it has been done, so this is the operation. So first, when the collision happens, suppose here the interaction point, suppose the heavy ion collision or the proton-proton collision happens here, the particles are produced at the center. So usually the collision vortex beam is tuned to have the collision at the center of the TPC. So then the particles which will started from the interaction point, they will be curved due to the magnetic field, and then this curved track actually will ionize the gas. And once the ionization happens, here you can see clearly here. So then the charged particles, the electrons will move towards the anode, and the ions will move towards the cathode. When the electrons will move towards the anode, so then you create a getting grid. So there is a cathode plane, there is an anode plane. So then this anode plane, when it comes near the anode plane, since these are wires, so the avalanche, so the electric field will be much stronger near the wire. So the avalanche will happen near the anode wire. But when what happens, avalanche means there will be a lot of electrons and the ions will be produced. So you don't want these ions to go back to the, again, your drift chamber where the ionization happening and the electrons are coming in this direction. To do that, so usually this getting grid is maintained at a high potential to block this ion flow into the other side. So this is the way usually it does, but then you have to pay the price in this case. Actually, this is a slow detector. So let me discuss how the tracking usually happens. So suppose if you look at this pad, so this is the cathode pad. In this cathode pad, you can see the signals will be collected here. So basically, this is segmented in X and Y. So this will give you the XY coordinate. This is in your end cap, which will give you the XY coordinate. Then if you know the final time and then the initial time of the detector, so that the delta T, the time difference, if you multiply with the drift velocity of this electron, then that will give you the Z coordinate in this axis. That is what basically shown here. These are the Z coordinates and then the XY plane. Basically, you reconstruct the track like this. But this is not so easy. First thing, you have to make sure that the drift velocity is actually constant. If it is varying with time, because the drift velocity has a dependence on your gas, the temperature and pressure of the gas, you have to maintain all this. So that drift velocity first needs to be measured. Usually we measure in the time projection chamber using a laser run, where you know the exact position of where the lasers are created. And from that, you can calculate the drift velocity. So once the drift velocity is known and the time difference, as you know, the initial time usually the first detector trigger detectors give, and when you collect the signal here, that gives the final time. The time difference delta T times this drift velocity will give you the Z coordinate. Basically, once you get this XYZ coordinate, you try to reconstruct this track. But here it is the only single track is shown. That is why you may think that it is easy. But in the real case, there will be thousands of particles which will be giving heat in your detector. So that is why you need an algorithm to fit those heat points and reconstruct those tracks. And that is usually happens in a Kalman filter. It is used, and then this will give you the global tracks. Once you find all the global tracks, then you try to project all these tracks to a common point, because they all should have generated from a single interaction point. But as in real case, due to resolution issues, spatial resolution issues, it may not project to one single point. So that may be sometimes will give you many tracks will project to one point. So that will be the one vertex. But there can be in single event also, there can be multiple vertices. So then you have to rank the vertex and find the best primary vertex and fit these tracks again, including that vertex. And that will give you the actual primary track of a primary track. Okay. So once you know the primary track, then the other information what we need is the momentum information. So as I said, since you know the magnetic field, how much magnetic field is applied, so the curvature of this track will give you the momentum of this particle. If it is a low momentum track, so it will be curved more. So then the similarly high momentum track will try to go in a more straight line. So the curvature, radius of curvature will be high. So that is how you can calculate the momentum of the track. In addition to that, so each anode plane actually you are losing some energy. So this energy deposition also you are measuring. So once you measure this energy deposition, you can calculate the average energy loss for this track, because this is a single track and this is expected to lose similar amount of energy at each point. But that does not happen, because every time the energy loss is a statistical process, and this ionization energy loss. So due to this energy straggling, that is called the statistical energy loss, is called energy straggling. So there will be at some point some more, some point higher, but it is not actually a Gaussian distribution. So it will be a Landau distribution, which I will talk about little later. Okay, so this is general introduction. So once you know the ddx of the particle, then you can compare with the theoretical ddx value, which I will discuss in next few slides. And then you can identify these particles. So let us start with the time projection chamber for start, because let me give you the geometry and the configuration of the time projection chamber in star. So TPC is in star is the primary tracking device, which is a volume of 4.2 meter in length and 4 meter in diameter. You can see this is 4 meter in diameter and the length is 4.2 meter. And the central membrane here, it is around minus 28 kilovolt it is applied. And then the readout system, as I said, so this has a 12 sectors in each side. Okay. So in each end cap, these are sectors. Individual one is a sector, but there are inner sectors and then outer sectors. Okay. So these inner sectors and outer sectors are actually the readouts are very different. So each inner sector consists of 13 paired rows, whereas outer sectors consist of 32 paired rows. That was the old design. Recently, it has been upgraded. I'll come to that part. But let us start with the analysis which we have been doing with this old data set. That was with 13 inner paired rows and 32 outer paired rows. And as I said, this is just one sector, and each side you have 12 sectors. So here this side 12 and the other side also 12 sectors. So these are based on the principle of multi-wire proportional chamber, which we discussed in the previous slide. So this readout was based on multi-wire proportional chamber. Okay, and the gas, which is the active volume in this detector, that is the P10 gas, which is nothing but 90% of argon and 10% of methane. So one can ask why we need to have this type of combination. That is because, so always you need a gas which will not, then the ionization will be produced efficiently, as well as for photons, which will be like the discharges will be produced, the photons will be produced, that will be absorbed by this quenching gas, that is the 10% of methane. So usually these inert gases are used in the gaseous detectors, and also, so the operating voltage is also very high here. And the uniform electric field, as I said, from the central membrane cathode to the anode in the, you have a 135 volt per centimeter is maintained throughout this detector till the readout. Okay, so that the electrons will move in the straight line. Okay, this is about time projection chamber for star. Then similar principle was used also in Alice. So Alice was also a detector which was 5 meter length and 5 meter diameter, and it has a gas volume of 92 meter cube. And instead of argon, they had used neon, carbon dioxide, as well as nitrogen of the percentage of 86%, 9%, and 5%. This mixture was used because these are the gas we optimize for better efficiency and a better resolution. So then there are highly segmented readout sectors here. So basically you have a 18 inner readout sectors and similarly 18 outer readout sectors in each side, and then similarly 36 this side and 36 also other side. And they have, each sector contains around 159 paired rows. So that means in the previous case it was 45 paired rows in the star TPC, but here it is 159 paired rows each sector consists of. So that is why the readouts are almost like 500,000 pairs readouts we read in the TPC. And there, here you can see the central part is the inner field cage, the outer field cage is this part, and that is what you try to maintain a uniform electric field, and the magnetic field also applied parallel to the electric field. So now, we now know how to reconstruct the track. So once we reconstruct, we can calculate the momentum of the track. Now let us see how to identify the particles. So as you all know, identification of the charge particles can be achieved in the TPC using the energy loss, that is the ddx. So this ddx means energy loss per unit length. So as I said in Alice TPC, so there are 159 paired rows. Suppose a track originates from the interaction point and goes through whole TPC. So this is a high momentum track, so it goes through whole TPC. So then it has to go through all 159 paired rows, and it will also deposit energy in all 159 paired rows. But if you plot that energy ddx for all 59 paired rows, this will give you this type of histogram. One ideally would have expected a Gaussian type of distribution. But what happens, sometimes there are delta electrons and which will lead to more energy loss. That is why in this case, instead of a Gaussian distribution, you will see a Landau type of distribution, which will have a long tail. So then that does not give you the correct energy loss for this track. Okay. So to get the correct energy loss, what actually we do? So we remove this higher energy loss part. So that is why it is called a truncated mean. So this is the most probable value instead of mean value. So you remove this 40% in Alice, actually removes 40%, in star it removes 30% of this higher energy loss. Then whatever remains, then you take the average of that. So that is the average energy loss for a track. So this energy loss, actually, if all of you have studied particle physics, you must have known this. And the energy loss of a heavy charge particle actually followed, described by the Bethe-Bloch formula, which tells you this is mostly the collisional energy loss, okay, the ionization energy loss. And it has a dependence on the incident particle. So if you look at what are the dependencies, first thing, it will depend on the charge of the particle. If it is a heavier charge, so it goes as a z square. That means if it is a charge state 1 or charge state 2, it will have energy loss different. Higher charge state will have a higher energy loss. Similarly, it goes 1 by beta square. So 1 by beta square means, so if the momentum of the particle or the velocity of the particle is higher, the energy loss will be lower. Okay. So if similarly, if it is lower, then the energy loss will be, velocity is lower means energy loss will be higher. And then there is a logarithm term also. So logarithm term also has a beta square dependence here, you can see. So that means, so the other terms I'll explain, but here now let us look at, so at a low energy or the low momentum, this term dominates. As you go to the high momentum region, then this is the term logarithm term, the relativistic rise we call it. Relativistic rise part also contributes. So that will be, energy loss will be much more, because at some point there is the minimum ionizing particles, so all the particles will lose similar amount of energy. Okay. So this is the relativistic rise part. And then there is a correction here. The here it is the density correction, as well as there is also sometimes there is a cell correction. The cell correction contribution is very small, but this density correction value is appreciable at a higher momentum. Okay, so that is what it is taken. So looking at this formula, so from this one can easily guess that this energy loss of this particle will depend on the charge of the particle as well as the momentum, or the mass, that is momentum is nothing but mass times velocity. So that means if you have the same momentum, different mass particles will lose different energy. So that is what actually we see in time projection chamber. So what I have shown here, so this is the time projection chamber from star detector, so which measures the ddx in the units of keV per centimeter, and this is P by Q, because usually you don't know the charge of the particle, so you basically measure the magnetic rigidity. So that is P by Q. If you plot it, you can see clearly there are bands, but there are a lot of particles which are in between the bands, but there is separate bands for particles. So on top of that, if you plot this theoretical curve, theoretical Bethe-Bloch curve for the detector material, which is called parameterized Bethe-Bloch function, because depending on the, if you look at this Bethe-Bloch formula, it depends on the Z and A of the material, which material you are using. So that is why, so you need to consider also this ionizing potential also depends on the active material which is used in TPC. So in our case as a gas detector, so, and it is also combination of few gases, so you need to modify this Bethe-Bloch formula for that. So these are the theoretical curves, Bethe-Bloch lines for the different particles. So you can see the pion band is this one, because the pion theoretical curve goes through it, and similarly K1 is going through it, and proton, deuteron, and then this is helium-3, and this is yours, the Triton, similar the antiparticles also in this side. Okay, this is the way actually we identify the particles. Similarly, if you look at ALICE also, the same thing is also done. So the P by Z, and here is the DDX in arbitrary units. So then you can see all the bands are clearly separated. And if you take a particular momentum, suppose you take 0.5 GV by C, so then you can see the pion, kaon, photon all are separated. But as you go to the high momentum around 1 GV, then you can see they are overlapping with each other. Then it is very difficult to use TPC to identify this pion, kaon at an intermediate PT region. So that is where the time of flight comes into play. Okay. So now let us discuss about time of flight. So since already we know that there are some limitations in the time in the identification of particles using time projection chamber, now we'll go to time of flight. So the time of flight detector, so it as you from the name it suggests that it measures the time of flight. That means it measures the time difference between the collision event when the collision happens and the time of arrival of the particles in the detector. So this is usually provides the particular identification, good particular identification at intermediate PT range. And this is a gas detector, which is based on the multi-gap resistive plate chamber. Instead of for two potentials like high voltage negative potential and positive potential, you can have intermediate, this resistive plates you can have. And then that way what happens, this electron does not have to travel the whole distance. So what it will when the electrons will move from the negative to positive side, so they will create the avalanche near this multiple resistive plates. Okay, so based on this principle, so one can calculate. So if you know the initial time and if you know the final time, so you also reconstruct the track using the TPC and extend it to the heat in the top and get the path length of that track. So by measuring the time of flight T and the path length L, then one can calculate the mass square by using this formula, or you can calculate the velocity, which is nothing but L by T, or the beta, which is V by C. Usually one can plot that. Also, if you want to calculate mass square, you can calculate the momentum is usually you get from the TPC, and this time of flight from the top, and the path length also using TPC and the top heat you get the path length, and then using this formula you can calculate the mass square. So in STAR, this time of flight detector consists of 120 trays. So it's usually 60 trays on the east side and 60 trays on the west side, like that. So it covers the full azimuth and the pseudo rapidity range plus minus 0.9. And there are 32 MRPC, this multiple resistive plate chambers in each module, each tray, and that is placed in this Z direction. So each tray has a 32 MRPC modules, and each module has a 6 readout systems. So this is the one module has this is 6 readout systems, the readout channels we call as. And in this case, for time of flight in STAR, we get the initial time from the 2 VPDs, which are installed at 5.4 meter from the center of the TPC. So this vortex position detectors actually give you the initial time, and their resolution is very good, of the order of a nanosecond level in the STAR. Okay, so you get that initial time in the from the VPD and the final time from the time of flight. And then using that time difference, that delta T, then you also calculate the path length and then calculate the velocity. And similarly in the ALICE, so this is also covers a pseudo rapidity range of plus minus 0.9 and with a radius of 2.7 to 3.99 meter. And the basic unit of this top system is a 10 gap MRPC strip. That means 5 strips on both sides actually it is used, and then it consists of 90 modules and are arranged in 18 sectors in phi and 5 segments in the Z direction. So this is the 5 segments in the Z direction, and then there are 18 sectors in phi, and it has about almost 160,000 channels. And this also uses gas for this isobutane and then C2H2F4 and SF6 gas mixture, and it gives good time resolution of the order of 40 picoseconds also it gives. Yeah, so then if you use time of flight, so then one can calculate beta. As I said, beta is nothing but V by C, or V you can calculate just path length divided by time of flight. So here the left hand side is the 1 by beta, usually star plots 1 by beta as a function P by Q. So you can see, so these are the theoretical curves, because you can always calculate for each particle mass. If you know, then you can calculate how the 1 by beta will vary as a function of P by Q. So then you can see these are theoretical lines, and these bands corresponds to, this is pion, this is kaon, this is photon, helium-3 and deuterium, like that. Similarly, in the ALICE also, this is in 2.76. This is the time of flight beta as a function of a momentum. Okay. So here basically here you can see electron band, pion band, kaon band, proton and deuterium bands clearly separated. So in ALICE usually they use n sigma top, which is basically the time measured by the minus time expected by the time the stop resolution, and that is how it is this n sigma value cut you can use to identify these particles. Suppose here you are using the time of flight for a pion, you use pion the resolution, the sigma, and similarly for kaon proton you can use, and the n sigma value for pion, kaon, proton you can calculate, and you can identify. I will come to that. So here is the particle identification technique. As I said, there are two detectors which are complementary to each other. So basically you calculate in the time projection chamber, and so ddx as a function of P by Q. So as I said, if you just plot this in z variable, so z variable we plot, or n sigma, if you plot also n sigma, it will be just 1 by r, that is the resolution. Otherwise z of any particle you want to identify, that is the logarithm of ddx measured divided by ddx predicted. So this predicted comes from your Bethe-Bloch formula, modified Bethe-Bloch formula. And then if you plot it as you expect, so if you use the pion Bethe-Bloch formula, or the energy loss here as a theoretical value, then the pion peak will come around 0. So that is what, if you see here z pion is plotted, so then the peak is coming around 0, the pion peak. And the next peak is the electron peak. If you see, the electron band goes here, and the electron peak is here, and then the kaon peak is here. Kaon is in the positive side, because we are subtracting the pion ddx curve. So that is why from all these ddx measured values, we are subtracting the pion one. So except pion will be around 0, but the others will be at a positive value. So you can see they are positive values. Then what you can do, you can just fit it a multiple Gaussian. By fitting the multiple Gaussian, you can calculate the yield in each. So this is projected in a particular PT transverse momentum beam, and then you can fit it with the multiple Gaussians to extract the yield in a particular PT beam. So that will give you the number of pion candidate, number of kaon candidate. These are the raw candidates. Then you have to correct for the efficiency and acceptance correction. Okay. So similarly, time of flight, as I said, one can calculate the time of flight from the time of flight detector. Momentum you can calculate from TPC, and path length you can calculate it by joining the tracks from TPC to top. Then if you calculate, then you can calculate m square. If you plot the m square for each particle, this is the curve, the black curve is the one which you will get. Then to extract the yield, then what you have to do, so you have to get the expected m square value for different particles for pion, kaon, and proton. So then there you have to take the timing resolution and momentum resolution properly, so that you get this simulated peak, the expected mass per distribution for pion and kaon. And from this fit, you can calculate their raw yield for different particles. This is the way we identify in STAR and ALICE, both detectors, we identify this pion, kaon, proton particles Once you identify these particles, so you can plot. So not only once you identify, then you have to also do the correction for the efficiency and acceptance. And once that is done, then you get the corrected yield. So basically here it is the invariant yield plotted as a function of PT for a different identified particles. This is for 14.5 GeV. This is in the mid rapidity measurement. So pi plus, pi minus, k plus, k minus, p bar, and this different color markers shows for different centralities and which are scaled with certain values. Okay. So basically, once you get this particle spectra, now you can extract a lot of physics out of this. First thing you can do is you can integrate the yield d and dy. You can calculate. Also, you can also integrate d and dy, mean PT, all the ball particle ratios, everything you can calculate. As well as if you fit with some blastwave model, then you can calculate the kinetic phase out parameters by fitting simultaneous fit doing this pi kp with a blastwave model. You can calculate the kinetic phase out, and calculating the d and dy or the particle ratios can be yield or ratios can be also used to extract the chemical phase out parameters using statistical thermal models. Similarly, it is not only pi on photon, there are also some other particles like those particles which are short-lived particles. They can be also measured or reconstructed in this using this particle identification techniques. So suppose phi meson, which is a resonance particle, which decays almost near to the primary vortex, that can be just identifying k plus k minus and doing the invariant mass reconstruction and estimating the background. That is usually this is done in the same event. If you do the invariant mass reconstruction using this formula, then you can get there is a peak around to the phi meson, this is k plus k minus invariant mass around phi meson mass, but there is a huge combinatorial background. To estimate the combinatorial background, usually different techniques are used. One of them is the mixed event technique. Basically, you take one k plus from one event, mix with a k minus from other events. Sometimes you take it with multiple events to increase the statistics so that the statistical error on the background will be smaller. So this is one way for reconstructing the resonance. Similarly, phi, k star, other resonances are also done like this delta also can be done using this method. And similarly, weak decays like k short, which decays after certain traveling at a certain distance. So then what you can do? So basically, you have to reconstruct the secondary vortex for this weak decays. So basically, k short lambda, you will see that they will this V0 particles usually you call it. They will travel a distance, then they will decay to. So here it is lambda decaying to p pi minus. So once you identify these daughter particles, so you have to reconstruct the secondary vortexes and then doing their invariant mass and subtracting this subtracting their background, then you can get the actual lambda yield. So here basically it's similar way, k short lambda and then xi minus omega minus and their antiparticles all are reconstructed using invariant mass techniques, identifying their daughter particles and then reconstruct. So basically in this weak decay particles, V0 particles, you apply the topological codes, then most of the backgrounds removes, then still some residual background is there, so which can be reconstructed using either a rotational background method or a mixed event background method. So this is what here is mixed event background for all the particles. Once you get that, so then again you can get the particle spectra invariant yield as a function of transverse momentum for all these particles in the mid rapidity. That is how you identify. In addition to that, there are like light nuclei are also directly measured from this energy loss mechanism. So time projection chamber energy loss and time of flight, both particle identification technique can be used to identify the light nuclei. So that is how Starr had identified or discovered the anti-alpha candidates first time, and in 2011. So you can see here, basically as I already explained, this is n sigma ddx, which is nothing but 1 by resolution logarithm of ddx measured by ddx predicted, which is coming from the theoretical value. So if you do that, so you can see this is the n sigma ddx axis, and then you have the mass axis in this side. So basically you will see a scattered plot here. So around 0, there are helium-3 candidate, here helium-3, anti-helium-3, here helium-4 and anti-helium-4 candidates. So basically you can select in sigma certain values and mass square values to count this candidate. And if you see here, clearly there are 4 candidates well separated. In using only time projection chamber also you can identify. So this method was used to identify around 18 counts are identified using time projection chamber and time of flight detector. And similarly, the anti-hypertritons and hypertritons also can be reconstructed. Once you identify this helium-3 deuterium proton, then you can do their invariant mass reconstruction. And that is what this invariant mass reconstruction was done for hypertriton and anti-hypertriton. And once you have this identification, you do the mass distribution, you fit it to get the precise mass information, and basically you can calculate the mass difference. And this mass difference actually in first time was measured in case of a hypernuclear sector, and this was observed in that CPT is not violated, CPT symmetry is not violated in this hypernuclear sector of the order of 10 to the power minus 4 precision. So similarly, other Alice already measured also the light nuclei. So then there are recently there are upgrades happen, as I discussed already. So existing star TPC was upgraded in the inner TPC was upgraded. Basically, as I said, inner TPC we had only 13 paired rows. Now instead of 13 paired rows, these inner sectors were divided into 40 paired rows. And then since it was the readouts are increased, the coverage also increased up to 1.9 plus minus 1.5, and also you can assess low PT, that is PT around 60 MeV by C you can also measure. And this is operational from 2019. And in addition to that, there are also new end cap time of flight was also installed in 2019, which is also operational during the beam energy scan data taking. And a new detector for event plane measurement was also introduced, that is the event plane detector. So now, similarly in Alice also, recently before this long shutdown, before run 3, so Alice also upgraded, because now Alice will have the minimum bias rate will go up to 50 kilohertz. So with this multi-wire proportional based readout, it will be very difficult to handle this high rate, because as I said in TPC always the space charge is an issue. So that is why recently Alice also changed this multi-wire proportional based readout chamber with a gas electron multiplier. So they are using 4 layers of GEM detector. So GEM detector, using different layers of GEM detector, you can actually reduce the ion backflow, and you can also read much faster. So that is why they also change the gas combination here in neon, carbon dioxide and nitrogen, 90, 10 and 5%. And that is basically this upgradation already completed in 2020, and now it is already taking data in Alice. And now briefly, last part, I'll just quickly go through this photon multiplicity detector. So photon multiplicity detector is a PCR detector. So having fine granularity and full azimuthal coverage. What happens? Basically, if you identify, distinguish between photon and hadron. So there are 2 planes in this case. There is a charged particle veto detector and there is a pre-shower detector. So these both are gas detectors. So when a charged particle will go through it, you expect this charged particle will only hit a single cell, or not more than 1-2 cells. But when a photon goes through it, if you use between this CPV plane and the pre-shower plane a lead converter, as you know, lead converter, because this is a high Z material. So then the photon, these high energy photons will go through, because of the pair production cross section will be higher. So then these photons will produce the electron positron pairs, and they will also produce, these electrons will give brimstone photons, and this shower will produce, and that will give multiple hits in your pre-shower detector for a photon cluster. Then you can do a clustering algorithm, and depending on the energy deposition and the number of cells hit, and optimize to identify the photons and separate from the hadrons. Okay, so that is how.
So, Chitrasen, you're close to the end of your talk, I guess.
Yes. Yeah.
A few minutes left.
Yeah. Another 2-3 slides.
Yeah. Great.
Yeah. So this photon multiplicity detector was installed in STAR also. So as I said, this was completely made in India, and this was installed 540 centimeter from the center of the TPC outside the star magnet. It was outside the star magnet in the east direction, and covers a pseudo rapidity -3.7 to -2.3. And it has 12 super modules in a hexagon structure, and it has around 41,472 hexagonal honeycombs. And the gas mixture was used in this case, argon, carbon dioxide in a ratio of 70/30. And this was taking data till 2011 in STAR. And a similar detector also designed for ALICE with a little bit improvement. The gas was same, then it has a pseudo rapidity coverage 2.3 to 3.9, full azimuthal coverage, and it has 48 modules, so it was mostly rectangular shape, and the number of cells in each module was 4,608, and this also took data till 2018, and the analysis is going on. So some of the results obtained from this, basically, as I said, you can identify measure the multiplicity of the photons. So that is what dn gamma by d eta is plotted here for different centrality. This is gold 62.4 GB, and then the model calculations are shown from Hygiene and MPT. And similarly, if you do this dn gamma d eta with scaled with the n part as a function of eta minus beam rapidity, then you can see they follow some scaling, that is the limiting fragmentation behavior which we see in STAR. And these papers are published in this reference. And recently also ALICE results were published. So ALICE, we measured the photon. This is the n gamma distribution for different center of mass energy in PP collisions, 0.9, 2.76, and 7 TeV, and it is fitted with a negative binomial distribution. But if you plot here also, you scale this with eta minus y beam, you plot as a function of eta minus y beam, that limiting fragmentation behavior is not seen in this case, and which was not expected at this high values of eta minus y beam. Okay, so with this, my summary slide. So particle identification is one of the main strengths of the STAR and ALICE experiment, because this is very crucial ingredients to study the strongly interactive matter found in the ultra-relativistic heavy ion collisions. And this STAR and ALICE provides PID information of various experimental techniques. I focused on few of them, 3 actually I discussed in this mostly, but there are many other detectors, as I said, HMPID, high momentum particle identification, and transition radiation detectors. These are detectors also used for identification of the particles, as well as the silicon detectors also. And several studies based on these identified particles are already done, and many conclusions are drawn. And now more exciting results are expected to come with some new detectors, and the upgraded detectors are coming up. With that, I would like to thank both STAR and ALICE collaborators, and thank you all for your attention.
Thank you very much, Chitrasen. So now I will pass the thing on to Sandeep, who has been looking at the questions, and he will interact with the audience. He'll interface between the audience and you. Thank you.
Okay, thank you.
Thanks, Sorindu. Thanks, Chitrasen, for this nice, detailed, and insightful talk. So the floor is now open for questions. We already have a few questions in the chat box in the Zoom. So maybe I'll start reading out those. Meanwhile, if you have some questions, maybe you can raise the hand, and then we can go individually to each of you. So for Chitrasen, the first question from Sorendu. Has there been any work on using AI/ML methods to do PID in STAR or ALICE? Can this improve ID, especially at higher PT where the bands begin to overlap?
Yes, there are efforts, mostly in STAR. It is not very effectively we have done till now, but in ALICE there are efforts to use machine learning to improve, to combine this particle detection techniques from several detectors to make more precise measurement as well as to go more higher PT range. I also didn't have time to discuss. So there is also another technique in STAR is used. So let me see. So in the relativistic rise part also can be used for the identification of the particles. So as you go little higher PT, so then there will be a relativistic rise. So there you can see the clear difference. STAR also has explored that part. Using the relativistic rise part, you can also explore identification of the particles. Yeah, but yeah, machine learning is in the play now to identify the particles.
Okay, so it is already being used.
Yes, people are exploring that point.
I see.
Yeah.
Okay, so I see Saurendu has raised his
Just one question. Sorry, since I have a related question. So, are there, or I mean, does it show promise compared to this, or is still in the exploration phase?
It is. I'm not sure because recently I'm not following ALICE so closely, but it is not used any analysis as far as I know. But I have seen some work has been done on using machine learning for this. Yeah. In the exploration performance stage, I have not seen any result which has come and published in the paper. Yeah.
Okay. Yeah, Saurendu, you have a question? Okay.
This is a kind of a follow-up of my question.
Yeah.
Yes.
So I was, I mean, the 2 points that I saw where things could be a little hairy. One is that there could be a point, there could be some PT range where discrimination is hard. Okay, so I think about 3 GeV or something, 3 to 4 GeV, K pi or 2 to 3 GeV, somewhere around there, K pi distinction becomes hard. And that's before the relativistic rise.
Yes.
Okay. So I was actually asking about that region, whether some other technique helps. That's number one. And number two is, there's some things which are statistics limited, like your 3 helium and anti-3 helium. And
Yes.
there could more refined discrimination due to AI methods somehow help. Do you know of any studies?
At least this part, actually, we have in STAR, we have also tried to explore using this combined TPC and top, but as you can see with top also, it goes up to 3 GB, 4 GB. So basically, as I showed in case of something like this, combining both n sigma DDX and the mass distribution, one can try to explore this region. But yeah, machine learning, as far as I know, in STAR we have not used it for the particular identification. But yeah, in future we are going to do that. In ALICE, I have seen some efforts have been going on for improving the particular identification of high PT.
Thank you.
Okay. So the next question in the chat box is from Rishi. Is the larger error bar on helium anti-helium difference in ALICE compared to STAR mainly because of statistics?
So this one, yeah, so this actually the mass difference which they had observed, the mass difference, yeah, it is mostly statistics because STAR has combined all these data sets and to get this one. get the mass measurement for helium-3 and anti-helium-3. I think that is mainly because of that. Yeah, statistics difference.
So statistics.
Yeah.
But so isn't don't we expect to produce more of these particles at Alice than at star?
Yes, we can means we are expected to produce at higher energy more particles, antiparticles. So, but with the current statistics, this helium-3, anti-helium-3 means they have a large error bar compared to us.
Or is this the difference? Maybe because at LH it is more net baryon 0, so that maybe the difference is smaller. Is that the thing?
But if you see there are errors, uncertainty is also larger.
For each of them.
Yeah.
Okay. So this is then identification technique. Is that the thing?
No, identification is very similar what we are doing. And this one, which is helium-3, anti-helium-3, I think in star we have combined the statistics for 262.4 all the data sets. So that is why our error bars is small.
Okay. And so there is another question from Rishi. In the fixed target mode, are TPC and TOF still important, or only the forward ones matter?
Still, the mid rapidity means TPC is still used main detector, but half of TPC you can say kind of used for this purpose. Yeah, the coverage, the means the acceptance changes with the beam rapidity.
The acceptance, okay.
Means the acceptance in the pseudo rapidity. Because you have fixed the target in one side, so the particles will go in the forward direction only. So that is why the whole TPC is not used.
Okay. So I don't still see any other hands raised. So if there are more questions, please, this is the time to ask. Meanwhile, I can ask one of my question. So so suppose in some calculation I need to look at the particle ratio, say proton by antiproton. Okay, this is just an example.
Okay.
The important thing is this baryon anti-baryon. Okay, but it could be something else. So, but usually when I look up the data paper, I will see proton and antiproton measurements separately, right? With some errors quoted.
Yes, yes.
Okay. So then usually what we do is when we take the for the ratio, we will add the errors in proton and antiproton in quadrature, right?
Yeah, yeah. So we propagate,
Yeah, but so my question is, so these errors that you quote for proton and antiproton, these errors consist of statistics as well as some systematic uncertainties, right?
Yes.
So, so is it correct to assume that these systematic uncertainties are uncorrelated for baryon and
yeah, that is a good point. Actually, star till now in many of the analysis you have not separated the correlated and uncorrelated error, but at least a few analysis they have done it. So slowly I think people are trying to quote separately the correlated and uncorrelated error, because when this type of ratio you need to calculate, you have to remove the correlated error.
Yeah.
Otherwise you are overestimating the error.
So you're saying this is being done but may not have yet come out.
In star we have not done that way till now.
Okay.
But at least I have seen some analysis this error is separated.
Okay. Okay. So maybe Rishi, can we now